I'm going to do is give you an updated version of the tutorial I gave at NIPS. So if you came to my NIPS tutorial in 2007, there's some new bits, but it's mostly the same as the NIPS tutorial in 2007. And what you'll learn about is an efficient way to learn multi-layered generative models from unlabeled data by learning one layer features at a time. That's basically the main content of the tutorial. That's it. That's what you're going to learn about. You'll learn about ways to extend it to have Markov random fields in each layer, that is lateral interactions. How to make, having learned these deep nets, how to make them work well for discrimination and classification, and how to combine them with modern kernel methods like Gaussian processes. How to use these methods to do explicit dimensionality reduction on very big data sets, and how that can help with things like fast document retrieval. And also how to apply the same methods to sequential data for making background characters for movies, for example. So to start with, I want to draw a distinction between two types of machine learning task. There's what I think of as typical statistics, where you typically have low dimensional data, maybe less than 100 dimensions. There's often a lot of noise in the data. There's typically not much structure in the data. So typical thing would be, say, some medical statistics on who died after a certain heart operation and who didn't. And you have sort of their blood pressure and their age and stuff like that. And the main problem is not thinking that the noise in the data is real structure. So financial prediction typically is in this range where it's almost all noise. Perhaps it's all noise. Artificial intelligence is the other end of a spectrum where you typically have high dimensional data. This is for sort of perceptual artificial intelligence. There's a lot of structure, and the noise isn't sufficient to sort of completely obscure the structure if you look at things right. And the problem is to have some representational scheme that's powerful enough to be able to represent the structure, but simple enough to allow you to learn it from data. So typically what we have is we have methods that will learn from data, like the EM algorithm, but without very powerful representations often, or methods that are very powerful like classical AI representations, but you don't know how to learn them from data. So a little bit of historical background. I'm going to trash neural networks in 3 slides. In the 1960s, people developed perceptrons, late 50s and 60s, and this is what a typical perceptron looked like. You had some inputs, and I'll mainly focus on processing images, so let's suppose these are pixels. You had some features that were designed by hand. These could have been little bits of computer program, but you could also think of them as perhaps fixed feature detectors. And then you learned weights connecting your features to decision units, and there was a very nice guarantee that if you did things in a simple way, you were guaranteed to find a set of weights that would always make the right choice if any such set of weights existed. And the problem was, in an architecture this simple, for complicated problems, there'd typically be no set of weights that could do the job, so the guarantee was rather vacuous. Nevertheless, people like Google use this kind of algorithm a lot on big data sets. What I think of as the second generation of neural networks allowed you to learn multiple layers of weights. That was seen as a big breakthrough. You could learn the strengths of the connections in multiple layers. And the backpropagation algorithm, which was invented by lots of different people, you start with an input vector, and you go feed forward through a neural net. You compare the output that you get with the correct answer, and then you take some measure of that discrepancy and go backwards through the neural net, computing derivatives for all these weights. I'm not going to go into the details of how you do it, but it's essentially just the chain rule. And at the time it seemed very exciting because it seemed we could learn multiple layers of representation, and indeed on toy problems we could, but it was rather a disappointment when used on big problems. And it basically has been supplanted in the 90s by support vector machines as a sort of method of choice for tackling some problem you don't understand. So you could think of the support vector machine as having, instead of having hand-coded features, taking training examples, and for each training example, automatically creating a feature. This isn't the sense of feature that they talk about when they talk about very high dimensional feature spaces. It's the sense of feature that perceptrons have. So you turn each training example into a feature, and the feature is essentially how similar is a test case to this training example. That's the value of the feature. And then you have a very clever way of eliminating most of those features, and simultaneously, as you do this elimination, figuring out the weights to put on the other features so as to make a sensible decision. And it turns out that works depressingly well. But it's just a perceptron, and it doesn't have multiple layers of representation. It has to be the case for big complicated problems. Multiple layers of representation are going to be a win. I'll try and convince you more of that later. What's wrong with backpropagation? The reason it can't compete with support vector machines on many of the tasks it was tried at, or doesn't do any better at least, is it requires labeled training data. And getting big labeled sets is tough. The learning time doesn't scale well. It's slow in deep networks. And deep networks often get stuck in poor local optima. I mean, they're much better than random, but we now know that, because we've got better ways of training them, deep networks can find much better optima than you find by just doing backpropagation from the labels. So the idea for overcoming those limitations, but within the framework of neural nets in a very loose sense, is we're going to try and keep the efficiency of doing learning by doing gradient descent in some cost function. But it's going to be a different cost function, at least to begin with. Instead of trying to model the probability of a label given the image, we're just going to try and model the probability of an image. That is, we're going to build a generative model of images, and once we've built this model, maybe it'll be able to say that's a likely image and this is an unlikely one. The main purpose of building this generative model is going to be so we have these features that we can use for something else later. But there are also other reasons you might want to build it, like if you're monitoring a nuclear power station, you might like to just know that it's in some improbable state. And then you run. So throughout the 1990s, starting in the 80s, throughout the 1990s, people developed an area called graphical models. I'm going to use the term belief net to mean essentially a directed graphical model, which is acyclic. This term is not really very well defined. So here's an example of a graphical model where these are variables that can have values. These are the observed variables. And you assume that when you make an observation, it was generated by some model like this. And so there's three problems. One is, what's the structure of the model? I'll basically ignore that problem in this tutorial. A second problem is, if you think you know the structure of the model, that is how many units in each layer and how many layers, can you infer what states of these hidden variables probably caused these visible effects? It's going to be a probabilistic model, and therefore you're not going to be able to infer these things for sure. Indeed, there may be many, many different combinations of states here that might have led to this. But at least we'd like to be able to pick some likely combination, or maybe pick some hidden configuration with a probability that's proportional to how likely it was to have caused this, given the current model. That's the inference problem. And that's assuming that you know all the parameters that define how the states of these two variables determine the state of this variable. What these arrows mean is that these guys determine the state of that guy. The learning problem is, can we now adjust all these parameters so as to make this model more likely to generate the observed data? And so learning is going to consist, if you knew the structure, of setting these parameters to make the model likely to generate the observed data, and then perception is going to consist of seeing some data and trying to figure out how it was probably caused by this model, and then saying the states of these guys are my guess about the underlying causes. And then maybe if this one says tiger and this one says running towards me, then I do something. I'm going to use nets composed of stochastic binary variables for most of the tutorial, but I will talk about other kinds of variable later. So the stochastic binary variables, or Bernoulli variables, they get some input, which in the generative model comes from above. It's the sum of the states of the units in the layer above times the weights on the connections, plus some bias term, and they give some output. And the output's going to be a 1 or a 0. They're going to be stochastic units. The probability that it's a 1 is going to follow this logistic curve. So if the total input's 0, it flips a coin essentially. If the total input's big and positive, it's nearly always on. and vice versa. So this is just the standard logistic function that's also used in some backpropagation networks. So now when we try and learn one of these nets, one thing that is easy to do with one of these nets is if I tell you the parameters on these connections, the weights on all these connections, and I ask you, show me the kinds of things the network believes in, the kinds of examples it wants to generate, well, the parameters are going to include biases for the top level units. So using the biases of the top level units, I decide whether they should be on or off. Then knowing the states of these two units, I decide whether this one should be on or off. This one may also have a bias. And in parallel, I can decide whether these ones should be on or off. And then knowing the states of all these three, I can decide in parallel whether these ones should be on or off. So I can generate a binary observed vector. And I can do it again, and I'll typically get a different answer because it's stochastic. And so it's very easy by doing what's called an ancestral pass, just a down pass in this net, to produce samples of what the model believes in. That's easy. It's much harder to infer, given a sample that you assume was produced by the model, how the model produced it. And it's hard to even get any good guess about that. And that's because of a phenomenon called explaining away. So it's going to be very hard to learn deep nets like this because we can't even do the inference. And to do the learning, you need to be able to do the inference, at least approximately. But for now, let's suspend disbelief and suppose that we could do the inference. So suppose that we could infer some probable state of the hidden variables. We could pick a state in proportion to the probability that that was the state that generated the observed vector. Then the learning is very easy in a sigmoid belief net. So let's suppose we want to learn the weights coming into this unit I. These are the units in the layer above. Let's suppose this is some hidden unit. What we need to do is take our sample from the posterior, which gives you a binary state for each of these guys, and say what we want to do is maximize the probability that the observed binary state would have been produced by the states that were observed up here. And so the probability of producing the observed binary state I'll call pi. That's the probability that this is 1 given the states of these guys, which is just ignoring biases, is the logistic of the sum of these weights times these states. So that's the probability the units up here would have turned it on, pi. And we have some actual state for it, si. And so the maximum likelihood learning rule turns out to be change the weight in proportion to, that's the learning rate, the difference between its state and its probability of turning on, multiplied by the, I call this the presynaptic state, the state of the unit that's driving it here. And the reason learning is going to happen is because the state of this guy when you did inference doesn't just depend on what these are up to, it depends on what's going on down here. And so it typically won't be the same as the pi. And this will make it, the pi, more like the si. So the learning rule is nice and easy, but it's the inference that's hard. And I want you to have an understanding for why the inference is hard, because it turns out that getting rid of that problem in the inference is the whole secret of making these deep belief nets easy to learn. So let's suppose we have a very simple belief net. So this is a binary belief net. These are binary things. I've given them names. This happened to me in California. I was lying in bed and the house jumped. And I just assumed a truck had hit the house because I'm English. Actually, it was an earthquake. But let's suppose that it could have been either. Houses don't just jump. So by putting a bias of minus 20 there, you said the probability the house just jumps is about e to the minus 20. The probability of a truck hitting the house is much more likely than the house just jumping. Let's make that e to the minus 10 about, and an earthquake about the same. Let's suppose these are independent causes. That is, we ignore the fact trucks steer funny in earthquakes. So let's make these independent causes. So the most likely state here in your sort of prior distribution is that neither of these will happen. It's very unlikely that both of them will happen. And there's a small chance of e to the minus 10 of one happening and the other not happening. But because of these big weights here, if a truck did hit the house, then there's an even chance the house will jump, because that's a total input of 0. Similarly, in an earthquake, there's an even chance the house will jump. But you'd be very silly to explain the house jumping by saying there was an earthquake and a truck hit the house. You're appealing to two very unlikely things to try and explain this extremely unlikely thing. But the product of these two very unlikely things is just as unlikely as this extremely unlikely thing, so you don't win by doing that. So the posterior distribution over these hidden causes looks something like this, possibly with more 9s. The probability they both happened is very unlikely. This is given that you've seen the house jump. The probability they neither happened is very unlikely, because the house after all did jump. This might have happened, or this might have happened, and those each have a probability of about 0.5. So notice now, all the probability is here, so these two things are highly anti-correlated. They were independent in the prior, they're assumed to be independent events, but once you've seen that the house jumped, then if you believe this, you almost certainly don't believe that, and vice versa. That's explaining away. Pearl was the first person to make a big deal of this, and it's what makes inference difficult in these networks. And we're going to get rid of it. There's two ways to get rid of it. You just pretend it's not there, that's called variational methods, or there's a more honest way to do it, which is what we're going to do. So the reason it's hard to learn some deep belief net that has these layers of hidden variables driving the layers below until you eventually get to observe the data. Well, let's think about learning these weights here, just these weights here that go from the bottom layer of hidden variables to the observed data. In order to learn these, we need a sample from the posterior here. But the posterior here depends on two things. The posterior distribution of these vectors here. It depends on the data. I'll call that dependency the likelihood term. And it also depends on the prior. Okay, if the stuff up here said this unit never turns on, then that's that. It can't turn on even if the data would like it to. And you have to take the product of two distributions and then renormalize. The distribution that comes from here, which is the prior distribution over possible vectors there, and the distribution that comes from here, which I'll call the likelihood distribution, and you multiply them together and renormalize, and that gives you the posterior here. So it looks like to learn these weights, you need the posterior, and to know the posterior, you need to know all these weights here. Therefore, you're going to have to learn all the weights at the same time. And initially, when you start learning these weights, you're going to be doing something pretty pointless, because these are going to be entirely wrong, and so these won't be sort of heading off in the right direction. They'll be trying to fit in with this crazy prior up here. And so that looks really complicated. And indeed it is. Some methods for trying to learn all the weights at the same time are to use Monte Carlo methods to sample from the posterior. That is, we go round sampling individual units one at a time, or maybe a little bunch at a time, and updating their states to make this more likely to generate the data, but with the right sort of noise in it. And eventually, if you do that long enough, you can set up a chain so you get a sample from the posterior. And then you can apply the learning algorithm. But it's very slow. Alternatively, we can sort of ignore explaining away and use much faster methods for getting approximate samples from the posterior. And we can show that if you do that, I'm not going to go into variational learning here, if you do get these approximate samples, then you can do learning, in fact just the same kind of learning as we were doing when we got exact samples. And what the learning will do is it won't necessarily make your model more likely to generate the data, but it will improve something that's sensible. Essentially what it'll improve is how likely your model is to generate the data, that log probability, minus some measure of how inaccurate your inference is. Either it'll make the model better at generating data, or it'll make your variational sloppy inference be more accurate. It'll change the weights so your crazy way of doing inference actually works. This is much faster than that, but it's sort of not doing quite the right thing. And for the kinds of models I'll show you later, if you try learning them this way, it takes forever. If you try learning this way, it doesn't learn that well. So the sort of main point of this tutorial is to try and convince you there's been a breakthrough that allows us to now learn these nets efficiently, multi-layer nets, as generative models, not as discriminative models like we did with backpropagation. If you try and learn one layer at a time, thinking of it as a deep belief, as a belief net, then if it really is a multi-layer belief net and you're ignoring the layers above, you'll be doing inference completely wrong. And the learning will try, when you learn the lowest level of weights, it will try and make the causes independent. Because if you're learning it assuming it's a model with just one layer, that has independent causes in the prior, and the learning will try and respect that. And so it'll do the wrong thing. It would be much better if we could learn that first layer of weights. If we're going to try and learn these without learning those at the same time, in a greedy way, we somehow want something to stand in for this prior when we do this learning, because we know we're going to stick some complicated prior here on later. So we don't want to assume independence there, but the question is, can we find something to stand in for that that will allow us to do much better learning of these weights? And as you'll see, the answer is yes. And in order to do that, we're going to apparently go off at a right angle and stop talking about these multi-layer nets and talk about undirected models rather than directed models. And it was a sort of bizarre twist that by studying these simple undirected models, we suddenly discovered how to learn these deep directed models. So if you take these sigmoid sigmoid units, then you can hook them up into a belief net. Radford Neal has a paper on that in 1982. Or you could hook them up with symmetric connections in what's called an undirected graphical model, and that gives you a Boltzmann machine in general. And what we're going to do is take a very restricted version of a Boltzmann machine that makes the learning much easier, and that's going to form a module out of which we can later build deep networks. So Terry Sinofsky, from the earliest days of Boltzmann machines, said, Jeff, these things are never going to work unless we can modularize them so we can learn a bit at a time. And 20 years later, I finally figured out how we could do that, almost by accident. So here's a restricted Boltzmann machine. You just have two layers of variables: visible variables, a layer of hidden variables. You have symmetric connections, and it's a bipartite graph. These guys don't talk to each other, and for now, these guys don't talk to each other. Although it's quite easy to make these guys talk to each other, and we'll do that later. We'll have a marker of random field sitting in here. But for now, let's just have this simple bipartite architecture. And let's forget about multiple layers for now. So one nice property this has is that if I show you the states of the visible variables, the pixels, these guys in an undirected model like this, these guys are independent of one another. In other words, given the weights on these two connections, this has some probability of turning on if you know the states of these, and that's independent of whether these other guys are on. That's quite different from a directed model. So we can quickly and in parallel get a sample from the posterior here. So the inference problem is trivial for a restricted Boltzmann machine. It's a very nice property they have, unlike a directed belief net with one hidden layer. Of course, they give up something else, which is they've got a much more complicated prior, but we'll see that in a minute. So these nets are best understood in terms of an energy function. So this is the state of the visible units. This is the state of the hidden units. That's the energy of a configuration of the whole net. That is an assignment of binary values to all the hidden and visible units. And if we ignore bias terms, so in all the math I'll just leave out the bias terms to keep it simpler, or in almost all the math. The energy is bad stuff. So the goodness is this here, which is negative energy, which is the state of a visible unit times the state of a hidden unit times the weight between them added up. So if visible units and hidden units are on, and they have a positive weight between them, that's good and the network's happy. If it's got a visible and hidden unit on and there's a negative weight, that's bad and the network's unhappy. And the network will tend to go to states where it's happy, low energy states. One nice property of this energy function is if you differentiate it with respect to the weight, wij, then you get this very simple product of two states. So if you want to manipulate the energy of a configuration, if I want to change the weights to make the energy of a configuration lower, all I need to do is to change the weight in proportion to this. That's exactly Hebb's learning rule, or the simplest interpretation of Hebb's learning rule. Hebb was a Canadian psychologist, for those of you who've never heard of him. The only famous Canadian psychologist. he actually did experiments for the CIA, I think. Maybe I'm wrong. So you can change the energy by changing the weight in proportion to the product of the two activities, which is a nice simple learning rule. And so in one of these restricted Boltzmann machines, the idea is we want to manipulate the probabilities of visible vectors. I want to show it some vectors and say, make these probable. Make these the kinds of things the model believes in. And I can do that by changing the energies of configurations. And if I run one of these networks right, then using stochastic logistic units, then the probability of a joint configuration will be proportional to e to the minus this energy. So by lowering the energy, I can raise the probability of a joint configuration. And so now I can manipulate probabilities by changing energies, and I can manipulate energies by changing weights. That's just the product of the activities. So it looks like I might have a simple rule for manipulating log probabilities. So the probability of a joint configuration here is proportional to e to the minus the energy, but unfortunately you have to compare it with all other possible configurations to know what the probability really is. That's called the partition function, and it's an awful thing to have to compute. If you want to know the probability of a visible vector, you have to sum over all possible states of the hidden units. So sum over all h of this lot. And so it's very hard to compute this too, to explicitly compute it, because you have this partition function in it. Now I want to show you that there's a simple learning algorithm that's not very efficient. And the simple learning algorithm works like this. You take a data vector and start some Markov chain at the data vector. So we put an image in there. Using whatever weights you have on the connections, you activate your hidden units. That is, each one gets some total input. You put that through the logistic. That's the probability of turning on, and then you turn it on with that probability. Then we reconstruct the data. That is, we use exactly the same rule the other way round to reactivate the binary pixels. And we keep going backwards and forwards like that, running this Markov chain for a long time, until what we're getting here is what I call fantasies, or samples from the model. The chain will have run so long that it forgot where it started, and this will be the kind of stuff the model wants to believe in. So if you want to know what this model believes, unlike in a belief net where you just do a downwards pass and it's easy to see the kinds of things it believes, if you want to sample what this model believes, you have to go backwards and forwards forever, or for a very long time anyway. So it's quite hard to see what the model believes in. But if you could get this, then the learning rule is very simple. The learning rule says, in order to maximize the probability of an observed vector that we put here, put the vector here and measure these correlations, the correlations between the states of hidden binary features and observed visible pixels when you've got V here, when you've got a data vector here, and compare those correlations with the correlations you get when the model's just dreaming, when it's generating from its fantasies. And the derivative of the log prob of a visible vector is the difference of these correlations. So if you sum this over all if you average this over all the visible vectors in the training set, then this is the right learning rule to change the weights to make the training set more likely. So this is a beautifully simple learning rule. The first term here is responsible for raising this number, the log of this number, and the second term is responsible for lowering the log of this number, and that's the way you make V big. So it's the partition function that gave rise to this second term. Now, about 17 years later, I found a way to make it go 1,000,000 times as fast. You just go up and down and up again. And that's about 100 times as fast as, well, it's 100 times as fast as running this chain for 200 steps. But computers went 10,000 times as fast by then. So the whole algorithm was now feasible. And I could now train things like this. And it turns out this is not the derivative of the log likelihood. In other words, if we change the weights by the difference between the statistics you get, the pairwise statistics, when you give it data and activate the features, And the pairwise statistics you get when you take reconstructions of data and activate the features, that's not maximizing the log prob of the model producing the data. It is very close to maximizing something else, which I'll talk about more later, but it works. In practice, it works pretty well. And it's efficient. So we can now train models like this efficiently. So I'll show you a toy example, and then a slightly less toy example. We'll have a small image of a handwritten digit, and I think it'll be entirely examples of handwritten 2s. And so we show lots of 2s. And we'll start off with random weights on the connections, and then we'll activate some feature detectors based on this input from the image. We'll then reconstruct the image. We'll activate the feature detectors again. And when we first activate the feature detectors, we increment the weights in proportion to the product of the activity of a feature detector and the activity of a pixel. So that's Hebbian learning. Then we reconstruct, and then we decrement the weights. And one way of thinking about why, so that's anti-Hebbian learning. One way of thinking about why this is a sensible learning algorithm is, we want to make the model more likely to believe in reality, what really happens. And so when we increment the weights here, we're making this configuration be a more probable configuration. And then we ask the model what it would like to reconstruct. And of course the model would like to reconstruct something that it finds more likely than the data. And so what we'll have here, on the whole, is something the model thinks is better, according to the model, than the real data. And the trick is to tell the model, well, that's not better than the real data. I want you to make that worse. Don't believe in this, believe in this. It's a bit like a teaching technique where you say to the students, here's the truth, and then you say to the students, what do you believe? And the great thing is you don't have to look at their answers, you just say you're wrong. And if they update their weights when you show them the truth, and they downgrade their weights on whatever they said, if they believe the same as you, nothing will happen. And if they believe anything different, they'll eventually come to believe the same as you. Which, so long as the teacher's right, that's a very efficient teaching technique because you don't have to look at the answers. So if you apply that to a bunch of handwritten digits, you get feature detectors that look like this. They're a bit washed out, I'm afraid, but if you look at this one, you can see it's dark here, light there, and pretty grey there. And so light means big positive weights, dark means big negative weights, and grey means weights close to 0. So this feature detector is very happy if it sees a piece of a 2 here and nothing there, and it doesn't much care what happens there, although it has some slight bets. A feature detector like this one wants to see the tail of a 2 there. So they've discovered sort of local pieces, and if we look at how good they are at reconstructing 2s, then we can see that they've discovered features out of which they can synthesize 2s very well. So this is an example of the model looking at data that it didn't train on and resynthesizing it. So it looks at this, goes up and regenerates it. And you see it regenerates something that looks very like the original data. And it's making it by activating some subset of those 50 hidden units. It's just a toy example. 50 isn't very many binary hidden units. So it's converted this into 50 bits and then resynthesized it. And it does a pretty good job, because this is the kind of data it believes in. You'll see it's regularized things a bit. So this is a 2 that has a vertical tail, which is very unlikely for a 2. It's very rare. And it tries to make it a bit more diagonal. So peculiarity, and this 2 has a little bit sticking out there. It's sort of more or less got rid of it there. Now let's see what it does if you give it data it didn't train on, so the kind of stuff it doesn't believe in. You'll notice something about what it's doing. It's trying to turn everything into a 2, right? It's been trained just on 2s. It thinks the whole world is composed of 2s, and if you show it anything, it says, what kind of a 2 is that? And that's because the features it has are just features for making 2s. It's in a sense learned its own identikit for synthesizing 2s, and if you showed anything else, it tries to make it out of the 2 identikit, and it comes out looking 2-like. So if you ask what's the difference between a 3 and a 2, well, a 3 is not connected there, so it connects it up, and a 2 is not connected there, so it breaks the connection. And so it's turned this 3 into a 2. There's a pretty good template overlap here. If you put this image on top of that image, they'd agree in most places. It would say it's a pretty good fit. But nevertheless, it's clearly, it would like to see a 2 there. Okay. My standard model of this is George Bush, it's out of date now. It's George Bush looking at Iraq, and George Bush believes Iraq is composed of 2s, and so if you show him some data like this, he just sees 2s and doesn't understand what's really going on. That's perhaps because he runs the learning algorithm the wrong way round. So the way he runs the learning algorithm is you take the data, you interpret it, you imagine what the data would be like if it really fitted your beliefs very well, and then you learn on that. And if you do that, of course, you'll do exactly the wrong thing. Okay. So these restricted Boltzmann machines are an example of what I call a product of experts. So one interesting thing in computer science and statistics and AI is to ask, if I have some probabilistic models, how might I combine them? Don't say that to a Bayesian because they know the answer. But you could take some probabilistic models and you could average them, and that's a mixture. A mixture has a problem, which is that it can never be sharper than the individual distributions. So if I have a bunch of vague things and I mix them, I get something even vaguer. And if I want to end up with a very precise, very sharp probabilities, I have to have very sharp components, and then to cover a big high dimensional space I need a huge number of them. A product says don't average the distributions, multiply them together pointwise, that is average their logs, and then renormalize. And that's really what one of these restricted Boltzmann machines is doing. Each hidden unit defines a distribution over the visible variables, and when you use that update rule of the logistic, that has a sum inside an exponential, right? That's really a product. And so it's multiplying all these distributions together to get the distribution of the visibles. So you can think of an RBM as an example of a product model, and that's a more powerful way of combining probabilistic models of data. It's exponentially more powerful, in fact. But of course it's much harder to learn because it has this, because of the renormalization that you have to do, it has this partition function. And what we've done really is for this simple network, this RBM, we've got a cheap hack that allows us to learn it quite well and very efficiently. But there's another thing we can do, which is what we're going to do next, which is even more fun than taking products of models. We can take compositions of models, like f of g of x. And the way we're going to do that is we're going to say, let's make the latent variables of one model be the data for the next model. So the output of one model gets fed to the next model as its input. And that's how we're going to learn multiple layers of representation. And somehow magically, this is going to solve the problem of explaining away. Hopefully it'll seem a bit less magic later. So what we do is we first train a layer of features, as I showed you, learning an RBM. Then we take the activations of those trained features and treat those as if they were pixels and learn another layer of features. Now there's some sleight of hand going on here because in the examples I showed you, when I learned the first layer of features, I didn't actually use binary values for the pixels. I treated the sort of grey levels as probabilities. And we're going to do the same here. It tends to work faster if what you do is, having learned the first RBM, it's very important when you're learning it for the hidden units to be stochastic. So they can't convey information via real values. But once you've learned, then you can take data, and given an input vector, it determines probabilities for the hidden units, no noise yet, and then you use those probability vectors as the data for training the next layer. So in effect, you're showing the next layer the full distribution, because the distribution really is factorial, and so by showing it those probabilities, you're showing it the full distribution of the hidden variables given the data. Now, if we'd done it all with binary activations, which also works, it's just a bit noisier, we can prove that every time we add another layer, if we do it in the right way, we get a better model of the data. In fact, the first time we add another layer, we do really get a better model of the data, or the model doesn't change. The second time we add a hidden layer, so when we're adding the third hidden layer, all we can guarantee is we're improving a variational bound. So what's going to happen is we're going to have our RBM, and that gives some log prob to the data. We now add another hidden layer. That improves a variational bound, which also actually improves the real log prob. We now add another hidden layer. That improves the variational bound again. And each time we add a layer, unless we've already got a perfect model, we'll be improving the variational bound, provided we add it in the right way. And as you'll see later, the right way means the layer mustn't be small and the weights must be initialized right. And all of this is assuming that we're actually doing maximum likelihood learning, not this contrastive divergence learning. But the point of all this is not really that we're going to exactly stick with the right thing to do. We want to have a feel for why the learning is working. And once we understand why it's working, we'll sort of break all the assumptions of the proofs and make it work quickly. After we've learned, say, 3 hidden layers, the question is, what kind of model do we get if, when we learned a restricted Boltzmann machine. And then we said, let's treat the activations of these as data and let's learn another Boltzmann machine. And then let's do it again and learn another Boltzmann machine. So we've learned 3 separate models. We learned a model of the data, we've learned a model of the hidden activities, and we've learned a model of these hidden activities. And then we want to put them together to make one big model. And it was Yi Wei-Tei who realized the right way to put them together, or the right way to understand what we were already doing when we put them together, which is rather surprising. When you put them all together, you haven't got one big undirected model. You've got a model that's a Boltzmann machine at the top, but is a directed belief net below that. That's why the arrows go down here. And the green stuff is the generative model, and the red stuff is just a hack for doing fast inference, but that works very well. So, in order to make quite clear what I mean by saying the red stuff's not part of the generative model, let me say how I would generate a sample from this model. For the top 2 layers, I go backwards and forwards forever if I want to generate a completely unbiased sample. So that's definitely a Boltzmann machine and it's tedious. Once I've done that, I then take the binary state I got here and go chunk chunk, and that's an unbiased sample from the composite model. So the composite model is not a big Boltzmann machine. The composite model is a restricted Boltzmann machine and then deep belief net stuff, as many layers as you like. So what we've got now is a way of churning out lots of layers of deep belief net stuff by learning this undirected stuff in the other direction. It's kind of not the kind of thing you'd have thought of doing. We just started doing this and then realized what we were doing later. You wouldn't have thought of learning lots of layers of directed stuff in the wrong direction using undirected stuff. You'll see later why that's a good idea. So, I'm now going to go into some slightly complicated math, but then we're going to have a nice example. I'm going to try and justify what the greedy learning is up to and why it works, why you can learn a layer at a time like this. First, I need to get some sort of properties of factorial distribution straight. So, given the visible units, the distribution across the hidden units is factorial. That is, they're independent, the hidden units, given the visible units. The posterior over the hiddens. But if I now add up those posterior distributions, or rather average them over many different data vectors, what I get is something that isn't factorial. Just like when I take a mixture of Gaussians, I get something that isn't a Gaussian. Here, when I average these factorial distributions, I get something non-factorial. I'll call that thing that I get the aggregated posterior. It's the posterior distribution over the hidden units aggregated over all the data vectors. Here's one picture of what greedy learning is doing. We're learning some weights that connect hidden units to visible units. And these weights are doing 2 things for us. The weights definitely define, given a hidden vector, what the probability is of turning on each of the visible units. So given a distribution over hidden vectors, they define a distribution over visible vectors. In particular, given the aggregated posterior distribution, they define some distribution for the data, which won't be quite right. And so this is a kind of parametric model that, given this aggregated posterior, defines a distribution for the data. But the very same weights also define a prior over the hidden things. So there's two things that are different. One is the aggregated posterior that you get by putting in data and looking at the states of the hidden units. A separate thing is the prior that you have for this, defined by these very same weights. And the way the prior is defined is that, suppose I took a Boltzmann machine with these weights in, and I just went backwards and forwards for a long time, and then sampled this, that would be a sample from this prior. Notice I didn't mention data when I did that. It's just what the model would like to put here. If it's a perfect model, of course, it'll be the same as the aggregated posterior. So these weights are playing two roles if we view it in a directed kind of way. They're defining a prior over this stuff, and they're defining a probability of this given these states. So we could generate from the model by going backwards and forwards for a long time and sampling from this prior, and then doing it once more and sampling here. And the trick of the deep learning is going to be to say, we're going to keep this bit, we're going to allow the W's to keep defining that, but for this bit we're going to replace them by something else. We're going to take this term, throw it away, and replace it by something better, which is what we're going to get when we treat this as data and learn another Boltzmann machine with different weights up here. Okay, this is tough stuff to get the hang of. It's going to get easier later. So a way of saying that in an equation is that the probability of a visible vector is the sum over all the hidden states of the probability of generating that hidden vector from the model times the probability of the visible vector given the hidden vector. And so that defines the probability of a visible vector. And if you've already learned the weights that define both these terms, then what you could do is leave this term alone and go off and improve that term, and you'll get a better model for the data. And that's the trick of deep learning. Just to sort of keep you straight about what's factorial and what's not, in a directed belief net, like the earthquake example, the posterior over the hidden units is very non-factorial. Remember, it was truck or earthquake, but not both. They were highly anti-correlated. It's the prior that's factorial in a directed belief net with one hidden layer. In an undirected model, it's all the other way around. The posterior is factorial and the prior is not. And most people who do graphical models are very used to directed nets, and they're very unused to thinking about these factorial posteriors and non-factorial priors. But that's what we need for doing this deep learning efficiently. If you try and do deep learning of a directed net by learning little bits of directed net, so if I start off by learning this in the absence of this, because I haven't learned those yet, notice in the undirected net we had a term here and the same W's we used for this prior. If you learn with directed nets, you would typically have an independent prior here, factorial prior, and try and learn these weights here. But since these are kind of independent, the learning will put a lot of effort into trying to make it be appropriate for these to be independent. And that's silly because later on we're going to put more stuff in here and these won't be independent anyway. So it'll put lots of effort into trying to achieve something that doesn't need to be achieved anyway, and it doesn't work very well. Lots of people have tried this. You can do it, but it just doesn't work very well. Okay, now I'm going to give you an example of all this stuff, and then I'll come back to a bit more theory later. So we're going to learn a better model now of handwritten digits. We're going to have bigger digits from the MNIST dataset, which is a very standard dataset where you can compare with all sorts of other methods. We're going to first learn 500 binary neurons. We're then going to take the probabilities of activations of those neurons as data, and we're going to learn another 500 binary neurons. We're then going to take these probabilities as data, and we're going to learn a top layer of 2,000 neurons, but for this data we're going to concatenate it with 10 mutually exclusive neurons, called a softmax, a multinomial thing, that, so we have a 510 dimensional vector here, where one of these is on, and we're going to learn a model of that. So this top level thing is going to be a restricted Boltzmann machine that's going to be modeling the joint density of these feature detectors and the label here. But notice when we learned all this stuff, we didn't need to know the label. This was learned without knowing the label. Once we've done the learning, we're going to have an interesting way of modeling the structure of the data. So the data is these handwritten digits, and you can think of it as it's in a 784 dimensional space, but the digits form these low dimensional manifolds that have 10 or 12 dimensions. And the question is, how should you model that kind of structure? Well, the obvious way is to go down to sort of 10 numbers, but should it be 10 or should it be 12? And should it be the same number for 1s as it is for 2s? And what about 7s? Because 7s can have a crossbar, so surely they need a few more dimensions for that. So it's quite hard to do explicit dimensionality reduction. It would be really hard if you didn't know how many manifolds there were. And notice we can do all this learning without knowing anything about the labels. So an alternative is to say, rather than doing explicit dimensionality reduction, what we'll do is we'll blow things up into some high dimensional space like this, and in the high dimensional space we'll learn pairwise interactions that rule out most of the space. They don't absolutely rule it out, they just mean that most of this space is very high energy. So you can think of what's happening up here is when all these weights are 0, this is a flat energy landscape up here. And when this learns, what it does is it creates ravines in this energy landscape. One ravine per class, roughly speaking. And the ravines have the property that in the floor of the ravine there'll be 10 or 12 degrees of freedom. So you can go along the floor of the ravine without raising the energy. Those are all perfectly good 2s. I'm going to show you these ravines in a minute. You can't normally see ravines in 510 dimensional spaces, but I'll show them to you. As you go along the floor, you're getting good 2s, so you've got your 12 degrees of freedom in the floor. As you go up the sides, the other 490 dimensions, you're making worse things like adding random pixels or distorting 2s in ways they shouldn't be distorted and stop them looking 2-like. Now this is a much better way of dealing with data that lies on low dimensional manifolds. If you learn this without the labels, for example, you don't need to know how many manifolds, you don't need to know how many dimensions per manifold, the manifolds don't need to have the same number of dimensions as you move along the manifold, and the number of dimensions can be a function of the energy level. That is, if you're willing to go up a little bit in energy, maybe you can get some more dimensions. You can have the idea of allowable deformations of the 2, and then kind of not quite so allowable deformations of the 2, but things that aren't as bad as random. And in fact, maybe a 2 and some other digit could become almost the same class, so you can have classes merge and things. It's just a much better way of handling data with multiple manifolds. You go up in dimensionality and then squeeze out the excess freedom by doing this kind of learning.
Jeff, it's your intuition about the recoding that's happening in those, that you need 2 layers as opposed to just say 1 there.
Okay, 2 layers works better. So there's empirical results. I'll show you some more empirical results later. I can give you a rationalization rather than an intuition. Here's a rationalization. Suppose I wanted a generative model. In this RBM here, by using pairwise interactions, can create these ravines. You can't create ravines by pairwise interactions here because the interactions won't do what you want. But you can do it up here, and then we need a layer of hidden units to map these things to pixels. So if you do it that way around, it's just you somehow create the ravines here, and then you map them non-linearly to the image. That sort of justifies that architecture a bit, well, at least rationalizes it. Now, I also did some fine-tuning of this to make it be a better generator, and I'm not going to sort of focus on the fine-tuning in this tutorial. It turns out we can now learn these things without any fine-tuning and have them work just about as well. Certainly without this kind of generative fine-tuning. So this is in the tutorial, so you can go read it if you want. And maybe in question time you can ask me more about this, but I'm not going to dwell on it now. So now what I'm going to show you is what happens if we learn layers to model digits like that. Okay, So there's that same network. I actually programmed all of this except the interface. The very cool looking interface was done by an undergrad who looked at my demo and said, I could make your demo look much cooler. So here's the image, here's 500 binary features, 500, 2000, here's the 10 labels, here's the identities of the labels, 0, 1, 2 and so on. Here's some images that we can feed to the network. So let's first get it to do some perception, some recognition. We feed it a 4. And now what we're going to do is just run it boink, 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 like this, and see what it thinks. And we're going to run it as a stochastic binary network. So you see these keep changing, and these keep changing, and these keep changing each time we do it. But this never changes. It's very sure that that's a 4. Now if I run it faster, you'll see there's a subset of these that don't change much, like that one there. And you can see that if I run it fast. Your visual systems will do nice things for you. You see the sort of static subset popping out. I have a training in psychology, so we need to do a control experiment to make sure it doesn't always see a 4. Okay, so it saw a 5 almost all the time then. Of course, we can now be mean to it and give it things where it's not quite clear what they are. Like that. And you'll see it spends most of its time oscillating between 4 and 8, which seems pretty appropriate there. Occasionally it thinks it's a 6 or something. Let me give it one more because I like it so much. That's clearly either a 1 or a 7, or just possibly a 2. And since I programmed it and it's my baby, I want to point out that it's not so unreasonable that it occasionally thinks it's a 4, because a 4 could be like that, right? So most of the time it thinks 7 or 1. That was 1 and that was 7, and it ends up on 7. The fact that it ends up there doesn't mean anything. The fact that this example is in this row means that if you run it a long time and average, then 7's the most likely bet. Okay. So that's the net doing recognition, where we just go chunk, 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 chunk. It turns out you can do that stochastically in average here, or you can just do a mean field version. That is, you compute the real values here, and then the real values here from those real values, then the real values here and the real values here. Actually, no. You get to the real values here, and then using those real values, you explicitly compute the free energy of this network with different things plugged in there, which I'm not going to go into. And that has almost exactly the same level of discrimination performance as if you did the stochastic thing 20 times and averaged. So let's suppose we did the stochastic thing 20 times and averaged, because it's easier to think of.
Because the units at the top level, which are stochastic, do they actually participate in the recognition? You showed some.
These.
One. Yeah, so some of them are very, for a given digit, are very deterministic. Some are very stochastic. Is it really using the really deterministic ones, those ones, to make the?
Those stochastic ones are influencing the free energy quite a lot, and so they are influencing the way it discriminates. Yeah. It's not just ignoring them. Okay. So I showed you it doing recognition, but what's more interesting for this net is that it can also do generation. It's what I call a deep belief net. It's got this restricted Boltzmann machine at the top, and so we can go backwards and forwards here, and then we can go chunk chunk. And what I'm going to do now is just go backwards and forwards here. So that's all the causal things that are happening, and starting from some random state, but with one of the labels fixed, so we know what it should do. And you're just going to see its brain state here. But that doesn't mean much to you, this brain state. You can't tell, for example, that that's a whatever it is. So what I'm going to do, since I have a generative model, is I'm going to show you what this brain state means by going chunk chunk. So this is what's in its brain, and this is what it's thinking about. That's what's in its mind. So you have the brain up here and you have the mind there. And I'm serious about that. So I'm telling it to imagine twos. So all that's really happening is it's doing this. But in order for you to see what this brain state means, or this brain state means, I'm playing it out down here. So this is an energy surface with all these ravines. And I started at some random place, but with this unit turned on, and the 2,000 connections coming out of there, which are trying to lower the energy of the 2 ravine and raise the energy of the other ravines. So as it wanders about this space, eventually it will stumble onto the 2 ravine. It's nowhere near it yet. Once it gets into the 2 ravine, it'll stay there forever. Almost forever. It'll very occasionally flip to another ravine and come back again, because they're much higher energy than the 2 ravine now. So it takes about 500 iterations to be, it's firmly in the 2 ravine now. And now it's wandering around that 2 ravine. And you're seeing what the ravine looks like, so to speak. This is the best visualization you're ever going to get of one of these high-dimensional ravines, because I'm giving you something that's very meaningful to you that tells you what this state is, at least what it means. If I just flip that label to, say, an 8, and do it again, it's not really in the 8 ravine yet. And by about now it'll be in the 8 ravine, and then it'll stay there forever and show you all the sorts of different 8s it believes in. Well, it doesn't have long enough to show you all the sorts, but it shows you a whole bunch of different sorts. And this is the best generative model there is of handwritten digits. I don't actually know that. I just say that every time I give this lecture, and I'm waiting for somebody to say, no, there isn't. So-and-so has a better model, but it hasn't happened yet. I'll show you one more. So it's not really firmly in the 5 ravine yet. It's there about now. And it'll generate 5s without tops and all sorts of weird 5s. See, there's a very weird 5, but it's definitely a 5. And because it can generate these things, it can recognize them, of course. These are things with reasonably low free energy up here. Okay. So these are samples, if you just run that chain with 1,000 iterations between each sample, these are samples clamping different labels. So you can see that almost everything it generates looks like a reasonable example of that label. I mean, there's a few things that don't, like this, and you can see it generates a big variety of things. So here it's generating very weird things, but they're sort of 8-like weird things. These are examples that I found by saying, on the test data, which examples do you get right, but only just? Which are the examples you're least sure of, but you got right? And these are they. And so it shows you it's pretty good. If you look at all these 2s, if you try to do a template match to those, there's no template you could write down that would fit all those nicely. And for example, wouldn't fit that. So it got all these right, including ones like that one. Of course, that doesn't mean there aren't simpler ones that it got wrong. Here's its performance on MNIST if you compare it with other methods that don't know anything about geometry. So this wasn't told anything about the fact one pixel is near another pixel. So what you need to compare it with is not things like convolutional neural nets where you've wired in lots of knowledge about geometry, but things like a support vector machine that's just given this vector of pixels and told, learn. So this is support vector machines done by Da Costa and Bernard Shellkop, so it's presumably done very well. They get about 1.4%. These generative models, or things learned as generative models, and then fine-tuned with a generative learning algorithm, get 1.25%. As we'll see later, we can now do much better than that. And so they're beating discriminative models, even though they were trained generatively. And that suggests that, well, there's a sort of general principle, which is discriminative models will tend to beat generative models when it's a lousy model anyway. If you tune it discriminatively, it'll work well for discrimination even though it's not a very good model. As soon as you get good models, which are sort of accurate models of the data, then generative models ought to work as well as discriminative models. Now I want to make the reverse inference, which isn't legitimate, which is that because this is working better than a discriminative model, it means it's a really good model of the data. But don't remember that bit. Okay. If you are willing to put in convolutions and things, then after I'd done this, Marco Aurelio Ranzato and other people in Jan LeCun's group tried the same technique with convolutional nets, but where you did greedy learning at each level unsupervised first, and training those with backpropagation but with extra data too. They're giving these 600,000 extra training cases. They get to 0.49%. But if they do this unsupervised layer by layer pre-training, they get even better. So the phenomenon seems to go through to other things as well. So I'm going to finish this session with actually two things. A bit more theory on what's really going on in this deep learning, and a bit more theory about how to make contrast divergence learning work faster. So, this is a very interesting belief net, right? It's definitely a belief net, it's directed, but it's infinitely deep. And the weights at every level are the same. I mean, the layers are alternating because they're different sizes, and this is the transpose of that weight matrix. You can have, and the biases in equivalent, all the H layers would have the same biases and all the V layers would have the same biases. Okay, so that's a belief net. But if we try generating from it, let's look at what the generative process would be. These weights define a probability of V given H, and then the same weights define a probability of H given V. And so we do P, V given H, H given V, V given H, H given V, V given H. If we start far enough up, we've just alternated. So that's exactly the Markov chain we were running with the restricted Boltzmann machine. Therefore, the distribution we get here has to be the same as the model distribution that we get from a restricted Boltzmann machine. Therefore, it's the same model. It's got the same parameters. It's just, all I've done is I've unrolled the Markov chain and said we could generate data from the model like that. Okay, that's fine. But this is, we're going to get a lot out of seeing that undirected model with one layer of weights is the same as an infinite directed model with shared weights between all the layers. So if we now think about doing inference, remember I said when you do inference in a directed model, you get explaining away. So suppose we only had this much directed model. Okay? That would be like the earthquake example. We'd have these two causes and one observed thing. And if the two causes could both cause this observed thing, when we see the observed thing, it anti-correlates these causes, even though they're independent in the prior. So that's explaining away, and it's a problem. It makes inference difficult, and it means you can't just go chunk and get an unbiased sample here. But now let's have all this stuff upstairs. There's no more parameters because these are all the same parameters as those. Since these two are positive weights, these are the same weights here, right? And these two things have a single cause up there. Now, if we were really, really lucky, then the negative correlation you get due to explaining away here would be exactly balanced by the positive correlation you get in the prior due to the fact these have a common cause up there. The stuff upstairs is clearly going to positively correlate these, because when that turns on, these are both going to turn on. So the prior produced by all this stuff causes a positive correlation there. The explaining away in the likelihood term causes a negative correlation there. Now, if we just have one layer of belief net, then these are negatively correlated in the posterior. But if we have all this extra stuff up here, then we have to multiply the term that comes from the likelihood with the term that comes from the prior. We have to multiply those together, and they've got exactly the opposite correlations, and the net result is that these become completely independent again. So all of this stuff upstairs is exactly the stuff you need to completely eliminate explaining away here. So now we can learn this model with no explaining away, which makes it very easy to learn. Well, it's very easy to learn these terms because there's no explaining away there. Of course, the problem is that these weights are the same as those weights, so we also need to learn all these terms. And so the tricky bit is learning the right prior for this model. But at least it's easy to learn these weights. So inference now consists of taking your data and just going chunk, and all of these guys are independent in the posterior, because the correlating effect, the anti-correlating effect here and the correlating effect there cancel out. Then given these, you can do the same again, and so you can just go chunk, 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 and you can get an unbiased sample from the posterior. So this is a very special directed belief net. It's a directed belief net in which you can generate going downwards, and you can do inference using exactly the same Markov chain going upwards, and that'll get you a sample from the posterior at every level, and then learning should be easy. So in fact, if you remember the learning algorithm I had for a directed belief net, let's think about learning a weight here between unit j in this layer and unit I in this layer. The learning algorithm says, get yourself a sample from the posterior. Well, that's easy to do, we just go chunk. And given that sample from the posterior, do learning that says, take the presynaptic activity, this guy, and multiply it by the difference between what you actually had here in the data or the posterior if it was a hidden layer, that's this guy, and the probability that this sample from the posterior would have turned this guy on. Well, what's the probability that this stuff would have turned that guy on? Instead of computing the probability, we're going to sample with that probability, and so we can actually do an experiment. We're going to take this and say, do you want to turn him on? Let's sample stochastically. And that's what I call this, right? But notice we did that experiment already, because when we did inference for this layer, we're exactly taking this sample and going through the same weights the other way and deciding whether this guy should be on or not. So this state here is actually, this is a reconstruction, right? So this state here is actually a sample of this probability we need. So we can plug that state in instead. So that the learning rule for this connection looks like Sj0 into the difference between the actual state of Si in the data, Si0, and the top-down prediction from this posterior state here, which is Si1. So that's the learning rule for a directed belief net for this weight here. But of course this weight is tied to all these other weights. So we need to apply the learning rule here too. And the learning rule there looks like this. And the learning rule here looks like this. And if you look at all these things, that term, Sj0, Si0, that stays. But this term, Sj0, Si1, shows up again there, Sj0, Si1, but with the opposite sign. So that cancels. And this cancels, and this cancels. And it all cancels until you get down to infinity here. And so we get the idea that if you take this directed belief net and figure out the learning rule says you get all these derivatives here, and they all cancel out, and you end up with a correlation that you get here and a correlation you get up at infinity there, and that's the Boltzmann machine learning rule. And then you can ask, well, what about that contrasted divergence approximation we were making when we didn't run the chain for very long? Well, suppose these weights were small, this chain would mix rapidly. And if the chain mixes rapidly, then when you do inference, it's also mixing rapidly. So by the time you've gone through a few steps, then you'll be sampling from the distribution the model believes in. Now if you take a model and you generate samples from the distribution it believes in, and you ask it, how would you like to change your parameters? It'll say, I don't want to change my parameters. My parameters fit this data really well. So we know that if the weights are small, all these derivatives up here will all add up to 0. There'll be noise in them, but they'll all come to 0 on average. So we can ignore them. So we can say, let's ignore all these small ones, and let's just take this one and this one. So we'll take the derivative here and the derivative here. So that gives us just these first two terms here, which gives us this correlation minus Si1, Sj1. That's the contrast divergence learning rule. So it's equivalent to saying we're going to learn this deep directed belief net by ignoring the small derivatives you get up there, which seems very sensible. Now the best thing to do actually is, as the weights get bigger, go for a few more steps, so run your Markov chain a little bit longer. And you can actually monitor that because you can look at the size of these derivatives and see whether the ones you're ignoring are very small. Okay, so that's sort of explained the relation between the directed learning algorithm, this algorithm, and the Boltzmann machine learning algorithm for a net where you have the same weights at every layer, and it's an infinite net. Now, of course, what we can do is we can say, why don't I start off learning this, which is equivalent to learning this. These are the same model, because look, all the same weights. Once I've learned that, I'm now going to freeze some weights. I'll freeze these weights here, and I'll just keep this bit of the model. I'll say, okay, I now have a model of how this stuff gets turned into that stuff. And I also know by using the weights the other way around, I can do accurate inference. And now I'll take all these weights, and I'll untie them from these weights. So these weights are frozen. These weights start off from where they were already. So I've got the same model. This model is still the same as that model. Oh, sorry, as the previous model. But now, with all these tied together, I start learning all these as a model of this stuff. And so you can also think of this learning algorithm as, we're always going to have this infinitely deep directed belief net. We're going to start off by learning all the weights at the same time, in all layers at the same time. And gradually we're going to untie the higher level weights from the already learned lower level weights to give ourselves more parameters. And we're going to get a better and better model. So that's another way to justify what's going on in this deep learning. And it's an explanation of why things keep getting better. Now, the question, how many layers should you actually use? There's no simple answer. Yoshua Benjo's group has done a lot of careful experiments showing that more layers helps, up to about 4 at least. If you try messing with this stuff, changing the number of units in a layer by 50% doesn't seem to make much difference. It's fairly robust to that. There are theorems that say if you make the net deep enough, it can learn anything, any distribution over binary vectors, even if it's narrow. But this is basically empirical. You just mess around. And this is just to relate it to the first paper in which we talked about all this kind of learning. When I learn those weights in higher layers, the inference that I'm doing at the bottom level is no longer correct. Okay? So if I use the transpose of these weights to do inference, that's the correct way to do inference if these weights are all the same as these weights. As soon as I start changing these, the prior up here no longer exactly cancels the likelihood term here. But at least I started from the right way of doing inference as opposed to something that was hopelessly wrong, like in variational inference. And now, as I change these weights, they're actually going to be very unhappy if they make this be doing inference wrong. So this will stay pretty good. And it turns out that what you win by changing these weights to get a better model of this is always going to be more than you lose by the fact that this isn't doing correct inference anymore. I'm not going to go into that anymore. Yeah, in the last couple of minutes I want to talk about how to improve contrast divergence. Basically by doing something else instead, but we still call it contrast divergence. Where contrast divergence goes wrong is if I have, say, an energy landscape like this. Oops, that doesn't work. I have my data on some manifold like this. Here's the whole space. And this is what I want to be low energy. And so what we do in contrast divergence is we pick a data point, we start the model there, we say, where would you like to go? And it says, I'd like to go here. And we say, don't go there, go here. So make this higher, make this lower. And that's going to create a ravine along the data. But suppose that when we do this, when we say make this higher and make this lower, we accidentally make some point over here lower. Because these parameters are used for all sorts of vectors. And suppose that when we learn here, we also make this lower. We could end up with a big hole here that we never see. So we don't realize that actually we haven't got a very good model because our model really believes in this stuff. We have to run the Markov chain for a long time to see that. So is there any way we can run the Markov chain for longer to see this kind of thing? Well, that's what this is about. What we're going to do is we're going to take the data, we're going to activate the hidden units, and we're going to measure the statistics. And that's going to be one term in the learning algorithm. But in addition, we can have a whole bunch of particles, I call them fantasy particles, that are sort of wandering around in the data space, and each time you update the weights, you move all these fantasy particles by one step of the Markov chain, but you don't reinitialize them at the data. And that initially sounds like a bad idea. So here's a concrete example. You take 100 examples of data, you activate the hidden units, you estimate the gradient of the first term. You estimate the first term of the gradient. You also take 100 fantasies and you use those to estimate the second term. But that's very tricky because the second term should sort of model what's going on in the whole space, and these particles can't find all the modes in this space, you'd have thought. So it's very strange that with just 100 fantasy particles you can model this whole partition function. And the issue is, are these fantasy particles able to find all the modes and model a partition function accurately? I'm going quite fast here, but you'll get the slides. I'll put all this on the web. And the answer is that the learning makes the fantasy particles move around. So I have an analogy here. Suppose I wanted to get 3D shape from images. And I said, well, I'm going to study single images and figure out how to get the 3D shape. And a friend says, you know, it might be better to think about video sequences because that might be easier problem. I say, no. I don't even want to think about video sequences until I can get shape from single images. Well, it's obvious that's a mistake, right? The equivalent mistake here is to say, I'm going to get the gradient and then I'm going to do some learning. And I really want to get the gradient before I do the learning. Well, it's going to turn out that because your gradient is these difference of statistics, actually the learning is very helpful in getting the gradient. And the reason the learning is helpful is, if you think about it, if you have an energy landscape that looks like this, suppose on that energy landscape, actually, I've got some fantasy particles, and my fantasy particles are sort of sitting here. I'll draw those in red for fantasy particles. But my data is sitting over here. A Markov chain has a hell of a job getting these guys out of there and into here. What the data is going to do is it's going to pull down there. It's going to say, make this deeper, because I want to have more belief in the data. But the learning is also going to say, because fantasy particles outnumber data here, it's going to make this go up. So rather than getting the particles to jump out of the minimum, what the particles do is they actively make the minimum go up until they spill over into here. And that's because the learning is modifying the energy landscape. And so you can't analyze these things by sort of freeze the learning, freeze the weights, and then think of the mixing rate of the Markov chain. The Markov chain can have a horrible mixing rate, but if you put it in this learning loop, nevertheless these guys will spill out. So it'll get over barriers that are hopeless for the Markov chain. So I've pretty much said all these slides say. Oh, I have the same picture, right. So you can see here there's more data, here there's more fantasy particles. So this one will go up until they spill over into there. So, that's good timing. Here's the summary so far. Restricted Boltzmann machines allow you to learn a layer of features. The maximum likelihood learning involves running this chain for a very long time, but you can do this shortcut, and it works pretty well. We can learn many layers of representation by treating the hidden states of one RBM as the data for training the next one. That's a composition of experts. And this gives us good generative models, and they can be generatively fine-tuned with this contrasted wake-sleep algorithm I haven't talked about. And in the rest of the tutorial, after the break, then you'll learn how to do discriminative fine-tuning of these models to make them much better, how to combine them with kernel ideas so that you can actually learn a kernel that can then be fine-tuned, particularly when you have a small amount of labeled data and lots of unlabeled data. and then various applications of them. How to use them for dimensionality reduction so you can get efficient codes for searching for documents. I'll show you how you can search. Suppose I give you 100 billion documents and say, I would like you to find me 1 million documents similar to one of these 100, similar to one that I give you. I'll show you how you can do that in a millisecond. Actually less than that, but I'll show you basically how you can do it in no time at all. No, really, I will, honestly. And then I'll talk about learning generative models which have connections, lateral connections, and so are more powerful generative models. And then I'll make the lateral connections more complicated. I'll make them be gated by higher level units. And so we'll get a new kind of module that's much more powerful than a restricted Boltzmann machine and is going to be the answer to everything. That means we only just started using it and we don't know why it doesn't work yet. And then I'll show an application to sequential data. So that's the break, and we now have 15 minutes for questions before tea turns up. It was all perfectly clear? Okay, there's a lot I could say about that. It'll work pretty well if the weights aren't exactly symmetric. It'll also work pretty well if... Now, actually, the algorithm will work, it's just a bit slower. If instead of doing pure bottom-up then pure top-down, what you do is something that's more bottom-up, mainly bottom-up, and then a little more top-down, and then a little less top-down. So basically, if you have top-down, some top-down, and you average it with bottom-up, and you keep changing how much top-down and how much bottom-up you have, you oscillate those, the same learning algorithm works. It just gets a smaller signal, so it's slower. So you can imagine an oscillation which is oscillating the amount of top-down input compared with bottom-up input. I know this isn't exactly what you said, but this is trying to make it biologically feasible. And if you get an oscillation like that, then that will be sufficient to implement this kind of learning algorithm. It's probably the best I can say about trying to make it biologically plausible. When I was generating from it, yes. No, it works much worse when you're generating if you use real valued states. Yes, so when I mean real valued, I mean it's between 0 and 1, but you use the probabilities instead of the stochastic states.
Why is it? Is there any
It works fine for recognition, but for generation, it just doesn't explore the space properly. You need that noise to explore the space, and the noise level is appropriate for sampling with the right frequencies, different things of different energies. There's a version of this where you train the whole thing and use the whole thing without ever having any noise, and that's much faster to train, but doesn't work nearly as well. The noise really is important. At least having noise in the hidden units. Yeah. Well, remember, we don't want to move away in just one dimension at a time. You can do that. That's called pseudo likelihood, where you get each dimension right at a time. You take some data and you say, do I want this one, do I allow this one dimension to change? So we want to move in many dimensions at once. And there's just too much work to do if you were to actually take a non-infinitesimal step, because there's too many directions, right? So you get stochastic about it to sample. There is a method called score matching, which is much more like what you say, where you try and compute that curvature matrix and just use that directly. So score matching is actually equivalent to contrast divergence if your Markov chain consists of adding infinitesimal amounts of Gaussian noise, which is pretty much like what you were saying. That's called score matching, and it's a method by Arpo Huvarinen. Peter. These persistent chains, which keep on running, it's sort of harder to get them to work. They work better in the end. So basically, I want to have my cake and eat it.
But there are other ways you can have your cake, so you can inject some of your data into the chains every so often.
Yes, you can reinitialize the chains every so often to bring it back to the data. And we've tried that, and it doesn't seem to be a win. I mean, so if you do careful experiments, if you're going to run for a long time, it's best to use these persistent chains, where the fantasy particles, the only thing that's making them move around is the unlearning going on them. I mean, that's That's what I didn't understand before, right? That this unlearning is going to push them around anyway. Right. I understand exactly what you're saying. We're changing some weights to try and help this state. But every weight is changing a quarter of the states in the whole system. That is all the configurations in which those two units are on. So there's all sorts of other things happening as side effects of changing these weights. And so just the intuitive idea, let's change these weights to help this state and hurt that state. God knows what all the side effects are. Well, the math helps a bit with that. So this is your guarantee, basically, that if we were to run the chain to get fantasies, and then we were to change the weights by these differences, then that is the derivative of the log prob. So we are guaranteed to improve things. In other words, all the side effects on other data vectors, if you take a sum over all the data here, the side effects on all the other data vectors are taken care of. It won't, I mean, certainly if you do things like turning down the learning rate with time, it will converge. Yes. And it's because of this, right? It's because this difference really is the derivative of the log prob of the data. So it can't, I mean, it's really improving something. Now it's improving it in, there's noise here, right? So in this noisy sense, it's improving something. It's expected to improve something. Yeah. Okay, so if you're doing it stochastically, it would make sense to take multiple samples. For each data vector, take multiple samples of the first hidden layer. But if you're doing it where you're using the real valued probabilities, you don't need to do that. That's one of the advantages of doing that. Because the distribution of the first hidden layer is fully characterized by those real valued probabilities. You don't need to do any sampling to get the distribution. So sort of the right thing to do would be learn the first layer of weights, then go through all your data once, computing those probability vectors for the first hidden layer, and then when you want data for training the next Boltzmann machine, sample it from those probability vectors. And all that's perfectly feasible. It's just, it turns out, if you leave out the sampling step, it works faster and gives you a model that's almost as good. Exactly, yes. If you want all the math to go through, yeah. So if you want all the math to work, and you want to get this guarantee that when you do the freezing, when you freeze these and start learning those, you need to initialize these at these values, and therefore all the H layers have to be the same size. You could, of course, have extra units with 0 weights coming into them. That would all be fine. But then you better have them at all the layers above that. But I think of this as just the theory that's sort of giving you an idea of what's really going on. Once you've got the theory in place, you then publish a paper, and then you throw all that out the window, and you just get on with it using hidden layers of whatever size you feel like. That may convey to you my view of the value of theory. It's no, it really is helpful for understanding what's going on. Without this kind of theory, you wouldn't understand why it's more effective to learn a deep net this way than to learn a directed model one layer at a time. It really explains why you get that difference. But obviously if I made this a bit bigger, it's not really going to hurt much. And maybe if I make it a bit smaller, it's not going to hurt that much. So let's just get on with it and see if it works. Yeah. And let me say one more thing about that. Part of it is that we're doing stochastic gradient descent for the optimization. And so we don't have to sort of worry that by violating the conditions, somehow my algorithm for finding the weights will go all wrong. If we were doing convex optimization, maybe we would be a lot less cavalier about messing with this. So what you have to do here is you just have to go feed forward through the layers to recognize. So it's fast. It's as fast as a feed forward neural net. And
free energy computation at the top for the digit example?
okay, if you've got a limited number of classes, that's just linear in the number of classes. So for most classification problems, it's like that. In fact, if you're doing SVMs, you'd rather there were just 2 classes anyway. So that's not a big problem. Also, there's relatively efficient ways of doing it. More efficient than you might have thought. So, and what you don't have to have a big set of support vectors. So I think it's probably more efficient than SVM. It's certainly not less efficient. And it scales very nicely for learning very big data sets, because everything's just linear in the work you need to do is kind of linear in the size of the data set. So there's nothing quadratic anywhere. Yeah. That comes after the break. But yeah, the same story holds. It's just a feed forward net after you've learned.